All right, so what I would like to do now is prove the Riesz Thorin theorem. And I mentioned I probably wasn't going to do it, but in the context of what people are learning in Professor Zhu's course on spaces of holomorphic functions, I think it's actually quite important to prove it. So remember what Riesz Thorin is. It's basically if you have these P's and Q's here, and I should mention Q0 could be 1. Okay, and if we have a linear T defined on these nice simple functions that have support with finite measure, and if we define P theta and Q theta in this way, and we have this technical condition here, then we can basically interpolate between two LP bounds for T. In particular, we can interpolate between these two bounds to get the following result. And we put this to extremely good use when we proved Hausdorff-Young. Okay? So, right, so why is this proof important? Well, what you want to do, and you do, I've done this actually in some of my work, is you want to prove versions of this for whatever space you're interested in, whatever LP kind of space you're interested in. In particular, you often want to prove this for various LP spaces of holomorphic functions. So for example, you might want to prove a version of Riesz Thorin for the Bergman space, which, right, so I don't remember what notation, or don't know what notation Professor Zhu is using, but often it's AP. So remember what the Bergman space of the disk is. It's all holomorphic functions on the disk, where this integral here is finite. Don't really need that. And here A is just ordinary, two-dimensional area measure. So really this is a Riemann integral because F is continuous on the disk, it's holomorphic. Right, and remember the Hardy space, also holomorphic functions on the disk, where the supremum is finite. So it's almost like a circle version of the Bergman space, f of r e to the I theta, p d theta. And what I'm particularly interested in is the complex plane version of basically the Hardy space. Sorry, the Bergman space, the complex plane version of this AP here. And this is all F in, well, F entire. So holomorphic on the complex plane, where, well, you can't really say just the ordinary LP norm is finite. You can prove very easily that only the zero function satisfies that by Liouville's theorem. But what's natural is you integrate against a Gaussian. So this here, this is the complex plane, e minus p over 2 z squared. This is finite. Okay, so in all three of these spaces, what you want to study operators on these spaces is a version of Riesz Thorin. And there's a way to kind of abstract Riesz Thorin to make it easier to prove versions of Riesz Thorin for various function spaces, and that's called complex interpolation. It is a bit technical, so I'm not going to get into it, but really there's no, I don't think there's a very, very good place to learn this is Professor Zhu's book. Particularly, he does this in chapter 2. He discusses complex interpolation, and it's called complex interpolation because, like we're going to do, it uses complex analysis. Yeah, and you can kind of think a proof of Riesz Thorin is really like an introduction to the techniques and ideas used to kind of generalize, abstractly generalize Riesz Thorin in a way that makes it easier to prove a version of Riesz Thorin for all these spaces and any other natural space of holomorphic functions you want. And like I said, this is very useful in actual research. I've had to prove a version myself of Riesz Thorin for a variation of this Fock space right here. It wasn't terribly deep, but it's something I needed because I wanted to study certain operators, particularly Toeplitz operators on a variation of this Fock space. Okay, so enough of that. Let's get to the proof of Riesz Thorin. Okay, so as I mentioned, the really key tool to proving Riesz Thorin is maximum modulus principle. Well, really, it's this Hadamard 3 lines theorem, which is really a consequence of the maximum modulus principle. So what's the 3 lines theorem? And I think this was actually a prelim problem, basically. But so let's say we have the strip here, all z, where the real part is between 0 and 1. So let me draw that real quick. Go to a new screen share. All right, so draw the complex plane. So this is the real part of z is 0. Draw this vertical line. Real part of z is 1. So S is just going to be, well, yeah, everything inside here. All z, where the real part is between 0 and 1. Okay, so let's say F is bounded continuous on the closed strip. This is the open strip. We're excluding the 2 boundary lines. Let's say F is holomorphic on the open strip. So the claim is that if M theta is the sup of F on some line in the strip, so the line being the real part of z is theta. So I'll just draw a line corresponding to M theta. It's kind of annoying to have to go back and forth on Zoom, but anyway. So let's say we have theta here. Let me make this black. Let us draw this vertical line here. Okay, so yeah, so let's say here the real part of z is theta, and M theta is just the supremum of F along this line here. Right, because here we're looking at all z where the real part is theta. So I claim that for any theta, we can basically interpolate between F on the imaginary axis and F on, well, the line where the real part is 1 to get this M theta is less than or equal to M0, 1 minus theta, M1 to the theta. So M0 corresponds to, well, the real part is 0. that line, and 1 corresponds to the real part as 1, that other boundary line for S. Okay. Okay, so yeah, how do we prove this? Well, first of all, we can assume M0 and M1 are positive. If either one of them are 0, then it's fairly easy using the maximum modulus principle to show that F is 0. I'll leave that as a homework. Okay, so assuming M0 and M1 are positive, if we can prove this in the case where M0 is M1 is 1, then in general we can apply this special case to this new function big F. Okay. And so just to make things a little simpler, we can just assume that M0 is M1 is 1. And this reduction is a homework. If you can prove it in this case here, then considering, in general, considering big F applied to this case here, you get the general result. And just in case there's any ambiguity here, this is just e to the z ln of a, as usual. A is positive, so there's no need to choose a branch of ln. It's just ln of a positive number. Okay. Right, so we know on the boundary of the strip, okay, so just go back here real quick. Okay, so on the boundary of the strip, well, M0 is the sup of F on this boundary part. M1 is the sup of F on this boundary part. We're assuming those two sups are 1. So we know on the boundary of S, F is less than or equal to the maximum of 1 and 1 is 1. Okay. Okay, so we can assume F is bounded above and modulus by 1 for Z in the boundary of the strip. Okay, so what we want to do is prove that F of Z in modulus is less than or equal to 1 for all Z in the strip here. So in particular, we'll obviously then get that along this line here, because this line is in the strip, F of Z in modulus is less than or equal to 1 along this line. Okay, so this is our task here. Okay, so what we do is we want to use maximum modulus principle, but we really need a bounded domain to do that. So we do a little trick here. F is assumed to be bounded on the closed strip, so we let K be this supremum here, just the supremum of F along the closed strip. And I'm going to define this function Fn. It's cleverly defined, but we'll see why it's a good choice in a moment. F of Z over 1 plus K over N Z. So in particular, for fixed Z as N goes to infinity, it's fairly obvious that Fn goes to F, because this whole thing here just goes to 0. So it's F of Z over 1 as N goes to infinity. Okay, so first of all, let's see that this is holomorphic, that there's no issue with the denominator being 0, and it's not really too bad. So, so sorry, before I do that, our bounded domain we're going to use is just this rectangle here. So let's go to the whiteboard. Okay, so I don't know. Let's use yellow, because why not? Okay, so here is imaginary part of Z is N. So maybe that's not the greatest of color choices. I mean, anyway. Okay, so here, imaginary part of z is minus n, imaginary part of z is n. Okay, so if we're in the strip, but we're between minus n and n for the imaginary part, then we're just in this rectangle here. Okay, so we're just in this rectangle. So maybe get rid of, well, yeah, so actually maybe, yeah, I'll just get rid of some stuff here. That works. Okay, so Sn is just going to be, so sorry. Okay, so yeah, Sn is just what's here. It's everything in the strip here, but imaginary part is bounded between minus n and n. Okay, right, and so the beauty here is that if we have a fixed z in the strip here, okay, and we pick n bigger than the absolute value of the imaginary part, then z is in Sn. So for fixed, in other words, for fixed z in the strip, and for n large enough, z is also in Sn. I mean, it's fairly, these two yellow lines just kind of go up and down, and we capture more and more and more of the strip, so that the union of these Sns is the whole strip. Okay, so now let's get back to the proof here. Okay, so first of all, yeah, Fn is holomorphic on Sn for each n. Why is that? Well, look at the denominator and modulus. So on Sn, because we're in the strip, the real part of the real part of z is between 0 and 1. So in particular, this whole thing here is bigger or equal to 1. And so the modulus, the whole thing is bigger or equal to 1. So this denominator is far away from 0, so Fn is holomorphic on Sn. Okay, not a terribly subtle conclusion here, but we need to know that to use maximum modulus principle. And we also want to know what Fn does on the boundary of Sn. this actual perimeter, this rectangle, the boundary rectangle. Okay. Okay, well, so again, if z is in the closed strip, then the bottom is bigger or equal to 1, so that in modulus, Fn of z is less than or equal to f of z. That's true for everything in the closed strip, but in particular, if z is on the boundary, then f of z in modulus is less than or equal to 1. So that's great. We know that on these kind of boundary portions here, that Fn in modulus of z is nice, it's less than or equal to 1. But we need to know what f looks like in modulus in these two yellow horizontal lines. So let's do that right now. Okay. So if we're on these two horizontal lines, which is saying we're in the boundary of, so if we are not on the boundary here, but, so get rid of this. Okay, so if z is in the strip, let's say the closure of the strip, and absolute value of y is equal to n, then, well, just go back to here. X is still between 0 and 1. Well, actually, we don't even care. This is obviously bigger or equal to 0. So we just want to look at what's going on with the imaginary part. Well, the imaginary part is either n or minus n. Okay, so this is equal to k. Okay, so Fn of z, the bottom, 1 over the bottom rather, in modulus, is less than or equal to, this didn't come out too well, but it's all right. So yeah, the bottom, 1 over the bottom rather, is bigger or equal to k, as long as absolute value of y is equal to n. So we're on either of these two yellow horizontal lines. Well, the numerator, remember, k was picked to be the suprema of f on this closed strip. Okay, so we get this estimate here if absolute value of y is equal to n and z is in the closed strip. So the conclusion is that for any z in the boundary rectangle of Sn, modulus Fn of z is less than or equal to 1. So actually here, not that it really matters, but yeah, it's fine looking at the boundaries. Get rid of all this. But really we want the boundary of Sn. Right, so the boundary of Sn, and the imaginary part of z is plus or minus n. Again, it's exactly these two yellow horizontal lines. Okay. Okay, so get rid of this here. Okay, right, so yeah, again, the conclusion is that we have a holomorphic function on Sn, this nice open, the interior of this rectangle. On the boundary, Fn is bounded in modulus by 1, so by the maximum modulus principle inside Sn, Fn is bounded by 1. Okay, so as I mentioned before, for fixed z, as n goes to infinity, Fn of z is f of z. And for large enough n, z is an Sn, as long as z is an S. So thanks to this little trick here, f of z in modulus is this limit. If z is an S, z is an Sn for large enough n. Hence, we have this estimate right here. Okay. For any n large enough, because, well, z continues to be an Sn for larger and larger n, just based on the picture I had a second ago. So this is going to be less than or equal to 1, and that's exactly what we want to prove. We want to prove that this is less than or equal to 1 if z is an S. All right, so nice clever proof. I guess Hadamard came up with this proof.